Right. Sure. All right, let me stop this or get this out of the way. Anybody have any questions from Wednesday? So next week, Wednesday and Friday will be virtual. I gotta go to Atlanta for the Amazon ad thing that they did during class that day. I have to go to Atlanta, so both days, Wednesday. Well, you know what, we'll just do the whole week that way. So we'll just do the whole week virtual, yeah. Cause I gotta leave Monday. I think Monday or, no, I'm leaving Tuesday. So yeah, so we'll just do that whole week virtual. So we left off talking about degrees of saturation. And I want to do a couple more of these because there's a couple of rules I want to discuss. When you have halogens present, when you have group 5 elements present like nitrogen. So let's knock those two out. And then we're going to move on and start talking about some of the reactions. Well, we're going to do a little bit of nomenclature first and then reaction. All right, so here, the formula is C7H11Br, right? So H rep, we need to calculate that, H rep. And we need to calculate H molecule. Right, so H rep is going to be 2 times 7 plus 2. Is that right? It's going to be 16. And then H molecule is 11. Remember, H molecule is just whatever that number is in that molecular formula. So it's 11 in this case. H rep is 16. Now, you can see right away, when I take H rep minus H molecule divided by 2, it's going to give me an odd number or a fraction, and I don't want that. So anytime you have group 7, bromine, chlorine, fluorine, iodine, any of those elements in group 7, you have to subtract 1 from H rep. Okay? So, I'm going to write there here, group 7 elements. Subtract 1 from H. Anytime you have a group 7 element present. So now that's going to be H rep, which is now going to be 15 minus 11 over 2. I'm going to subtract 1 from H rep, which was 16. That's going to be 4 over 2. So the degrees of unsaturation for that formula is 2. What does that mean? If I have 2 degrees of unsaturation, what does that mean? It means I can have 2 rings, is that right? 2 double bonds, 1 ring and 1 double bond, so on and so forth. Because the degrees of unsaturation tells me the number of rings and or double bonds that are present. So if I have 2 degrees of unsaturation, that means I can have 2 rings or 1 ring and a double bond. So if I had to come up with a structure for that formula, right, well, there's a couple that I can think of, but let's do this. Let's see if we can do 7 carbons and then put 2 double bonds in and a bromine and see if it matches. Right? So we know we got the carbon and bromine, that's no problem. We need to count up the hydrogen. So this will be a CH3. This is a CH3, that's 6 right there. 7, 8, 9, 10, 11. This is an example structure for that formula. There are multiple structures you could draw from that formula. And they will all be considered constitutional isomers. Same formula, different structure. But I satisfy the 2 degrees of unsaturation here. I have 2 double bonds present. Right? You can also have a ring structure. The 7 carbons in the ring. Or 6 carbons with a carbon hanging off the ring. I mean, you can, as long as you don't violate Lewis structures, drawing the proper Lewis structures, you can have multiple structures with that formula. If that makes sense. So anytime you have group 7 present, when you're calculating degrees of unsaturation, you subtract 1 from the HREF. Let's look at F, because this is another instance where I have a group 5, I have a nitrogen present. So that changes the rules a little bit as well. Right, so HREF is 2 times 5 plus 2. So HREF in this case is going to be 12. Is that right? HREF is 2 times the number of carbons plus 2. And then H molecule is 9. That's whatever number is there. You can see right away, I'm going to end up with a fraction. 12 minus 9 over 2 is going to be 3 over 2, and I don't want that. So if I have group 5 elements present, I need to add 1 to HREF. So nitrogen, phosphorus, anything in that group. I would add 1 to HREF. So this is going to be 12 plus 1, which is 13. So 13 is HREF now because of the nitrogen. And the reason for that is that nitrogen can actually have a proton on it. It can have a hydrogen on it. You have to account for that. So anytime you have a group 5 element present in your formula, you need to add 1 to HREF. All right, so now this is going to be 13 minus 9 over 2, 4 over 2. All right, so I got 2 degrees of unsaturation here as well. All right, so a sample here, let's do this. Let's say we have a 5-membered ring with a nitrogen and a double bond. Because 2 means I got 1 of each. I can have 1 of each. I can have a double bond in the ring. I want to put the nitrogen here, that's NH2, and then there's 1 hydrogen here and 1 here, and then 2 here, 2 here, and then 1 here. That's 2, 4, 5, 6, 7, 8, 9. 9 hydrogens, 5 carbons, 1 nitrogen. All right. As long as your structure meets the requirements for a proper Lewis structure, it is not incorrect. Because if we just have a molecular formula, we don't know the structure. All right, questions? Any questions about that part? All right. Let's do, a couple of the nomenclature problems. And we'll start here, all right? Because I hate teaching nomenclature because it's so cumbersome, it takes a long time, but we're gonna work through the first example, and we're gonna work through 2 examples, under number 3. Then we're gonna start on the reaction. All right, so the first example says, give the IUPAC name for each compound. So IUPAC is a group of chemists, International Union of Pure and Applied Chemistry, or Pure and Applied Chemists. And they set the rules for nomenclature, they set the rules for different things within the sphere of chemical knowledge. So it's like a committee. So when we have a compound like this, anybody remember what we need to do first? Anytime we're trying to name something, anybody remember what we need to find? We talked about it, it's been a while, but we did talk about that in passing. The parent, we need to find the parent, is that familiar to you? Which is the longest chain that contains the functional group. So if we have an alkene like this one, we're gonna find the longest chain. So let's count from here to here. 1, 2, 3, 4, 5, 6, 7. And we're gonna count again from here. 1, 2, 3, 4, 5, 6, 7, 8. So we see now the longest chain is 8 carbons. So that's my parent. Are you following? And then since it's an alkene, so we're gonna find the longest chain. Second is you want a number from the end closest to the alkene. This is an alkene, right? So that's the rule. And that's closest to the double bond, that's where we number from. So we're gonna start numbering from here. 1, 2, 3, 4, 5, 6, 7, and 8. Right, so once we number it, then we can find the substituents. Anything that's not a part of the longest chain is attached to it. So it's not a part of the backbone, it's connected to the backbone. So we have a methyl group here. That's a CH3. Right, it's just written in skeletal form, so you don't have to write that out. We also have a group here. So 2 carbon chain here. So this is literally CH2, CH3. Anybody not following? All right, so what is 8? Anybody remember that? We think talking about carbon chains and naming them. It was a while back. So if you don't remember, I'm not overly frustrated. But if you do remember, that's great. Well, what was 8? Anybody remember what that is?
Octane.
I heard somebody say it. Octane, did you say octane?
Octane.
Okay, good. 8 carbon chain is a saturated chain is octane. When you have a double bond present, you have to change the ending, the suffix. So the parent in this case is going to be octene. Because the E tells me that there's a double bond present. Octene. See why this is why I don't like teaching nomenclature. There are a lot of rules and it takes forever to give you one example. But we got to do it. Well, we don't have to, but we're going to do it. So octene is my parent. Where's the double bond? What carbons are involved in the double bond? Hmm? What was the number? 2 and 3. So my double bond is between 2 and 3, but I'm going to give the lowest number possible. right? So this is 2 octenes. I'm gonna put a 2 right here. That's my parent, 2 octenes. The 2 is indicative of the location of the double, it's the address of the double bond. You always give it the lowest number possible. And then I have 2 substituents. I have a methyl and I have an ethyl. Right, the 2 carbon chain is ethyl, that's derived from ethane, which is 2 carbon. 1 carbon substituent is a methyl derived from methane. All right, so now we can add those in. What's the location of the methyl group? What's the address? What's the number of the carbon where the methyl group is? Is that carbon 2? What's the number of the carbon where the ethyl group is attached? 5. Right? When you list the substituents, they're in alphabetical order, regardless of what number is in front of them. So this is going to be 5 ethyl. That should be capitalized. 2 methyl. 2 octene. That's the name of that compound. So we found the parent, which is the longest chain, which is 8 carbon. So this is my parent, and then we have 2 substituents. So we have to list the substituents with their address. I'll always say that the naming of compound is kind of like you have a street name, which is 2 octene, that's the parent. And then if you have things attached to the parent, those are residents on that street. And they all have an address. Right, so the 5 is where the ethyl group lives, and then carbon 2 is where the methyl group lives, so on and so forth. So you find the longest chain, you number it, and then you find your substituents, right? And then you name it. All your substituents come in alphabetical order. Questions? Any questions about that? All right, let's go down to the next question. It says, give the structure corresponding to each name. I'm gonna start with the 2 bottom ones, because those are the easiest ones. Heptene means what? How many carbons are in that parent? 7. 7 carbons, right? And it says 2 heptene, but it also says trans 2 heptene. That means something. If you have an alkene, right, it can be trans, where the 2 groups on opposite sides, or it can be cis, where the 2 groups are on the same side. Y'all following that? So if both groups on either side of that alkene are on the same side, on the same plane, you can see that right here. And then these on opposite sides of the same plane, then one is trans and one is cis. So for trans 2 heptene, I need a trans double bond, so I'm going to write out heptene. So that's 7 carbons. And it's telling me that the alkene is at carbon 2. That's what the 2 means in front of heptene. So if I number this, 1, 2, 3, 4, 5, 6, 7. I'm going to put the double bond right here. And it's trans because this group is on one side and that group is on the other side. So that's the structure for trans 2 heptene. All right. Any questions about that? All right, let's look at the next one. 4 octene. For something like octene, which is going to be how many carbons? 8 carbons. And where's the double bond going to be in that alkene? Between which carbons? If the number preceding the parent is 4, which 2 carbons is that double bond between? 4 or 3. 3 would be lower than 4. So if it was between 3 and 4, then that would be 3 octane. But because 4 is there, that means it's between 4 and 5. Is that right? Because you always give the lowest number. Make sense? So let's do that. Let's draw the double bond first. You gotta make it 6. So this is carbon 4, that's carbon 5. So I'm gonna add carbon 6, 7, and 8. And I'm gonna add carbon 3, 2, and 1. So 3, 2, and 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. And 2 groups on the same side, so it's cis 4 octane. The trans and cis are, that's an example of what we call stereochemistry. Right, or the 3D orientation of a molecule. Right, that's what we mean when we say stereochemistry. It's the 3D orientation, how it's oriented in space. All right, let's do the first one. So it says 3,3-dimethyl. The parent is cyclopentane. What is pent? Anybody? 5. So there are 5 carbons, and the cyclo in front of pentene means that it's a ring. Do y'all remember that? We talked about that a while back. So the cyclo part means I have a ring, that's 5 carbons. I'm going to draw that out. 1, 2, 3, 4, 5, like that. I can put that double bond anywhere in the ring because it says cyclopentene. The ene means that there's a double bond present. I'm gonna just put it here. So that's cyclopentene. All right, if that's the case, for cyclopentene, if you have a double bond in the ring, the 2 carbons in that double bond are always 1 and 2. It doesn't matter which way you number it. The 2 carbons in that ring are always 1 and 2. So we'll number it that way. So that makes this carbon 3. Anybody not following that? So on carbon 3, what does it say in terms of the substituents? It says 3,3-dimethyl. So the di means 2. Remember that from back in August? I think it was August. Might have been September. The di means 2. The methyl means it's a CH3, and then 3,3 means that there are 2 of them at the same position. All right, so it's 3,3-dimethyl. So I'm gonna put those in right here. Right, anytime you have 2 of the same or 2 identical substituents, you always use that prefix di. You have 3 identical substituents, you'll use a prefix tri. If you have 4, you'll use tetra. If you have 5, you'll use penta, so on and so forth. Anytime you have an identical substituent, you have to indicate that with a prefix. Right? So di, tri, tetra, penta, so on and so forth. All right, questions about the nomenclature part? I know I blew through that, but feel free to ask questions. All right, let's go to the next section. So the next section, these are halogenation reactions. Right? So this is gonna be me adding the halogens to the alkene. I'm actually gonna cut this out, put it on another page. I don't wanna try to cram all this in here. All right, so let's take that first reaction. We're gonna walk through it, mechanism, arrows, everything. All right, this particular reaction is the addition of HX. Addition of HX to an alkene. The X is a halogen, so it can be HCl, HBr, HI. HF doesn't work, but it can be any of the other halogens. But normally it's just iodine, bromine, and chlorine because the reactivities of those are well known. And usually when you use that to make an alkyl halide, typically the alkyl halide is used for some other transformation. Maybe some type of coupling reaction or something like that. All right, so I'm gonna write out that alkene. So on one side of it, you have a carbon here like this. And this is like that. That's what that subscript 2 outside of parentheses. Remember that's like a condensed. Y'all remember that? Yeah, condensed versus linear. Condensed versus Lewis versus skeletal. So that would be the condensed form that's written above. And then a double bond is here. And then this is another carbon. This is H. And this is H2, CH3. Make sure you get that down. I want everybody to have it before I move on and do something else. All right. So this is plus HCl. When you write out HCl, make sure you show the bond, but that does matter. And all of the reactions that we're going to study with alkenes, the alkene itself is going to be a nucleophile. Right? It's going to be a nucleophile. So it's going to be attacking some electrophile. All right? Questions? Any questions about anything? All right. So here, I'm going to show it attacking. We've seen these arrows before. We studied nucleophiles and electrophiles. So the pi bond itself is going to supply a pair of electrons that attack hydrogen. All right. And then when I do that, I'm also breaking HCl bond like that. Right? When I do that, I'm actually breaking the pi bond. Right, I'm breaking the pi bond. Excuse me, and I'm also breaking the HCl bond. So over here, what we get next is very important, so I'm not gonna rush through that. That hydrogen is going to one of these two carbons, right? And the other one is gonna be positive. Right, every time this reaction happens, it goes through a carbocation intermediate. So let me show you the intermediate. I'm gonna abbreviate those, groups. All right, you'll see it. So let's say this is the hydrogen that came from chlorine, from the HCl, right? And this is my intermediate, and I'm gonna put a plus charge on this part. If I broke that pi bond, all of your additions of HX to an alkene are gonna go through a carbocation intermediate. Right? Why do you think, let me ask this question because we should be able to answer this. Why do you think the plus charge goes where it goes when you compare those two carbons? Okay, the plus charge could have gone to either side though. I understand what you're saying, and I agree with that to an extent. But that positive charge could be here or on the other side, and the H could have been here. But why would the positive charge want to be on a tertiary carbon and not a primary carbon or a secondary carbon?
Is it because SN1 reactions prefer tertiary carbons, or they're like stabilized by tertiary carbons?
Yeah, so we know that, right? We know the carbocation stability trend, tertiary is the best carbocation that you can make. So that leads us to another part of this discussion, which is what we call regiochemistry. Right, or the area, the carbon in a double bond, which picks up the proton. This actually follows what we call cont'd rule. I'll give you time to write that down. That's a lot of syllables. Right, follows more cont'd rule. Right, what that means is two things, right? We can define it two ways. We can say that the halogen from HX always adds to the more substituted carbon. The other way we say that is the carbocation always ends up on the more substituted carbon. Both things mean the same thing, right? So I'm going to say X always adds to the most substituted carbon. Right? Question. Question. So my common cause rule says that when I make that carbocation, it's got to end up where it's most stable, and that's where the halogen is going to go. So the next step in the reaction is to add the chlorine that we lost from over here. All right, so this is coming here like that, boom, coming right to that plus charge. And then I'm gonna have this as my product. Any questions about that? It's a fairly simple mechanism, but it has a lot of really important things embedded within it. Number one is my carbon cause rule, which you'll see again. Because there's the other regiochemistry that's counter to that is what we call anti-more carbon cause, which we'll talk about later. Also, as far as the alkene being the nucleophile, in this particular case, that's always going to be the case. It's going to attack hydrogen, break the HX bond, and then the halogen is going to end up coming back and attacking the plus charge, wherever that carbocation is. Any questions about that? Right, so if your alkene is substituted like this one, the more substituted side is usually where your halogen is going to end up. There's a way to do this where it's the reverse, but it's not common. And it goes through a radical mechanism also. All right, any questions about that? Anything about it? All right, let's do the next one. Let's do this one. The halogenation. So this is an example of halogenation. I'm gonna erase the chlorine and I'm gonna draw out or write it out. I'm gonna go through this mechanism also. All right. What this does is it adds a halogen to both sides of the double bond. Both sides of the alkene are gonna get halogenated. All right, and again, this reaction, the alkene is a nucleophile. So the alkene is going to attack chlorine. Right, and break the chlorine bond. So this is coming here like that. And I'm breaking that chlorine bond. Right, the mechanism for this is actually debated. It's actually thought that chlorine just kind of comes in like here, and then the attack is rapid, and then the chlorine comes and attacks here. But I'm gonna show you the traditional way of thinking about it. We're gonna stick with that. So when I do that, I'm gonna get this as an intermediate. 7 carbon, and we're using these 2 over here, so we put a chlorine here. Plus charge here. All right, this is really important because that doesn't stay like that. This is the most important part of the mechanism. Because it controls the stereochemistry, it controls how the other chlorine is going to attack. And it's still out here, but it doesn't attack right away. Right, so what happens in this case is the chlorine actually collapses down on that carbocation, and you make a little three-member ring, called a fluorinium ring, fluorinium ion. looks like that. Right? So let me ask this question, after you write this down, I wanna see what your thinking is. Right? If that chlorine that's in the ring closes down and makes this chlorinium intermediate, but you have a chlorine out here that can attack, which one do you think is faster? You got a chlorine sitting out here, and then you have a chlorine already in the ring, and this doesn't attack, like directly. You get to this before this can attack that. So which process do you think is faster? This one. This has to be faster than this attacking that plus charge. Otherwise, this would just attack right away, right? But it does, that's not how it happens. So the ring closure, this is, let me write down what this is. This is a chlorinium ion. So the ring closure is faster than direct attack of that other chlorine which is out here. All right, this gives us a chance to add another layer, another definition that is really important to know. This is, and this would be what we consider intramolecular. Right, I'm gonna write that up here. Intramolecular ring closure is faster than direct attack. Intermolecular. Right, slower than ring closure. Follow? Anybody got a question about that? So we get to this intermediate right here. And I'm gonna draw, I wanna highlight this, I wanna make sure you get it. Both of these bonds are wedged. Right? They're both wedged, coming out of the screen. The other highlight of this reaction mechanism is this. The other chlorine never attacks from the same side. Right? It always attacks from opposite of where those chlorine bonds are located. So if I had to draw this in 3D, I would draw it like this, so that the chlorine is here. Like coming up out of the page. So the other chlorine has to come from the bottom side. And that's what happens. So here's my other chlorine in here. Still kind of hanging, comes and attacks and pops that ring open. Okay, questions? So when that happens, one of my chlorines is going to be on a wedge, other going to be on a dash like that. The relationship between these two is what we call anti or trans. Always. Anytime you do a halogenation, if it's chlorine, bromine, or iodine, the two halogens always end up anti to one another. They're never on the same side. Always anti. And that's because of that intermediate. And that's how we can be certain about what the mechanism is, because if not, if it was just direct attack, then the stereochemistry will be scrambled. And trans and anti, that's a description of the 3D orientation. for the stereo picture. All right, any questions about that? I'm gonna stop here. I don't want to overload it for the day, because I think this is good for today, Monday. We're gonna come in, guns blazing. So I'm gonna send you some more videos over the weekend, but you don't have to watch them until after you take the exam, because you gotta take the exam. The exam itself is, this exam, you have to take in one sitting. Are you going out of town? So you gotta take it in one sitting, and you have, take 4 hours to take it. So once you sit down and take it, make sure you have a block of time set aside that you can take it and finish it. It's not a lot. But if you stop it, it's just gonna submit your answer, and you don't wanna do that. So set aside a block of time. It's not gonna take you 4 hours. I just gave you 4 hours just to make sure you have plenty of time to complete it. But you gotta do it all in one sitting this time. Gotta tighten the screws up a little bit. All right, any questions? If not, we're gonna stop here. You too. All right, take care. Y'all have a good one. Thank you.